So more and more people are living in cities nowadays in a much more high density environment, and it means that now the likelihood of picking up an infection from someone else is higher than ever. The hospital environment is particularly important in this context because it brings together lots of people with infections, but also lots of people with compromised immune systems. So the likelihood of picking up something from within the hospital environment is higher.
The real issue now is that we're having patients surviving longer. We're having much more complicated patients that we're managing to support through and be made healthy. The risks for them long term from these organisms is much greater.
The perfect outcome is to give to Greater Ormond Street Hospital a filter that will actually destroy bacteria, which will destroy viruses, and give very good filtration so that these bugs can be prevented going into the air and the water.
The filters that we're developing are specifically designed to work with hospital water systems and air systems, which can spread around pathogens or dangerous microbes between the different patients. Initially, what we do is embed the antimicrobial nanoparticles within the fibre mesh itself. The nanoparticles are embedded within the fibres, and then they can come into contact with the microbes as they pass through. The next step is to then incorporate the filter into the water pipe. The flow of the water will go through the filter. As the microbial cells flow down the water pipe, they will then come into contact with the filter and the antimicrobial nanoparticles within it, and this contact will basically kill the cells. We have a really wonderful team of experts working on this project. The University of Hertfordshire working on the nanoparticles, UCL Mechanical Engineering manufacturing the filters for us, and Great Ormond Street Hospital who have provided the need for the project.
Our responsibility is to try to test the materials, their physical properties, their biological properties. So we're trying to produce a nanoparticle and a nanoparticle suspension. The first thing we need to solve is to disperse nanoparticles into different systems so we can use them properly.
So it is very important to break them down as small as possible so that we are maximizing the surface area of this nanoparticle. This is important again because it allows the maximum surface area interaction with the microbes.
Once we have this dispersed system, and we shifted this part of nanoparticles to the UCL, and the UCL will put them into filters and test the filters at their lab.
So we get given the nanoparticles from the University of Hertfordshire. They're given to us in suspension. We then add those into a polymer solution and process that into ultrafine fibres using pressurized aeration. So in this lab we're essentially turning a solution into a filter.
Our aim is to make a very thin filter that will eliminate the bacteria over prolonged periods of time.
This process is called pressurized aeration, and it marries centrifugal spinning with solution blow spinning, leaving behind just very small fibres.
We are looking at the pressure and the rotation speed decreasing the size of the fibre, and the flow rate having sufficient flow so that we get a very good woven fibre.
These unassuming little things are actually microfibres, and we can get them all the way down to nanoscale depending on the conditions and the polymer we use.
Once the filters are made here, we send them off to UCL Civil Engineering where the antimicrobial properties of the fibres are tested, and we test them in light conditions, so we also use apparatus that mimic water and air filtration conditions.
We are testing the antimicrobial filters that have been made at UCL Mechanical Engineering. So what Claire, my postdoc, does is she uses a sort of rig that we've had built, which is much like a tap. So the flow of the water is a similar sort of flow rate as you'd get in a tap, and what she does is put a suspension of bacteria within the water and then pass it through the filter, and she'll take a sample of bacteria before they've been filtered and after they've been filtered and see what the difference is in the numbers of live cells and dead cells. I think what I particularly enjoy is coming up with solutions to real life problems, and also working with people from all sorts of different disciplines to come up with a solution together. I think that there's real strength in that because we're basically powerless on our own.
We're all complementary. we can't do the whole thing ourselves, and we have to join everything together to tackle this antimicrobial resistant problem.
I'm just so privileged to be able to do something with people that when I turn around and go, this is what keeps me awake. Being with people who I know that I can come with the myriad of really complicated issues. You know, healthcare is a complex environment that I can turn around and go, this is my problem. Have you got a solution? And they can go, yeah, actually, I've got this that I was thinking of doing. It's been eye-opening, and it means that you learn skills and you pick up information that I can then take back to my clinical practice and actually change things in my day-to-day, which is what it's all about.